Okay, so we saw how when you go from one basis to another, representations of operators undergo a similarity transformation, right? So there are some special kinds of similarity transformations which we can take your representations into a very special form, right? So in order to go there, so we look at a class of invertible matrices, right? In this lecture, we'll look at a class of useful invertible matrices, and which we will come in handy in our discussion of this transformation, special kind of basis transformation, which we will discuss ahead. Okay, so if you take some set of linearly independent n column vectors and just stack them together and form an n by n matrix, right? So we'll argue that such a matrix is going to be invertible, right? So what I'm saying is I start with some n column vector, so I have a bunch of numbers here. So then I choose another vector which is linearly independent, meaning it's not just some multiple of this. So I have another vector made up of n elements. Then I have a third vector made up of again n elements, which is each of these three vectors linearly independent. The fourth one then I pull out, that is also linearly independent, so on. If I put together exactly n such vectors and then form a an n by n matrix, so I have some coefficient all the way up to n, exactly I have n columns and exactly n rows. But the key point is that each of these vectors is linearly independent. So linearly independent, I have n linearly independent vectors, right? So if I am able to do this, then I am guaranteed that such a matrix is invertible, right? That's the statement. Okay, so yeah, so I'm showing it again. So I denote these vectors. I have a vector x1, which is, I will call these elements s11, s12, so on up to s1n. In general, the ith vector will be si1, si2, all the way up to sin, right? So we are given these vectors x1, x2, all the way up to xn, and what we are given is that all of them are linearly independent, and so we form this matrix s11, s12, all the way up to s1n, s21, s22, all the way up to s2n, and so on. Now the assertion is that this matrix S is invertible, right? So how do we argue for this? It follows from our understanding of the rank of this matrix, right? So we know that the column rank of such any matrix is the same as the row rank of any matrix. So if you look at, there are n column vectors which are all linearly independent, and we have seen that the column rank is the same as the number of linearly independent column vectors. So there are n of these. Therefore, this matrix is, the row rank is the same as the column rank, and the rank of the matrix is n. Every row and every rank carries information that cannot be got from other ranks. There is no way to take linear combinations of rows or columns of this and then reduce it to a effectively a lower number of rows or lower number of columns. Every column is essential, right? That's what it means. We have seen this, and we have played with these ideas in the past, right? So you can go and review some of these results if you're confused. But the point is that since there are n linearly independent vectors, it's a matrix of rank n, and that means that none of the eigenvalues of this matrix can be 0. Because if it were 0, then it would mean that its determinant is 0, and if it's a determinant 0 matrix, then it cannot be a full rank matrix. It has to, then you have to look for submatrices of dimension n minus 1 and so on, right? That is one prescription we gave. Another way to think about it is that if an eigenvalue is 0, then at least one of these rows is sort of redundant. That's what is meant by some eigenvalue, one or more eigenvalues being 0. And for sure, if none of the eigenvalues is 0, determinant is non-zero. It's an invertible matrix. So as you have also seen, the inverse of a matrix will contain a factor of 1 over the determinant. And if the determinant is 0, then it's not invertible. But if the determinant is non-zero, then 1 over determinant of this matrix is not a problem. Okay, so why do we care about this? So you will see that this has an important application. With this, we are interested in forming matrices, which are got by stacking together a bunch of n column vectors. Now there is a special kind of linear dependent n column vector, right? If you had stacked together not just n linearly independent n column vectors, but also those who are mutually orthogonal, right? Like for example, when we are doing Gram-Schmidt orthogonalization process, that's what we are doing, right? You start with a vector, then you get another vector, and then do some tricks to make the second vector orthogonal to the first one. You start and orthonormalize them, in fact, right? And then you take a third one which is orthogonal to both the first and the second, and also you normalize it, right? And so on. So if you do that, then we have a stronger result. In fact, if you take a set of n mutually orthogonal n column vectors and stack them together to form an n by n matrix, then this resulting matrix is not only invertible, but in fact it's going to be unitary. You can read off its inverse, right? So it's kind of a remarkable and sort of a very beautiful result that this happens, right? So you're working with some Gram-Schmidt orthogonalization process, and then you find one vector, you find a second vector, third vector, so on. It's not such a surprise that you can make a bunch of vectors which are this guy is orthogonal to this, normalized orthogonal to this, and then this guy is normal to the first two, and so on, right? But let's say you have worked this way and you have come up to n minus 1, and then you put in one more vector, and then suddenly you have not just one set of orthogonal, orthonormal set of vectors, but in fact you have suddenly created one more, because it's like somehow a jigsaw puzzle which fits together in such a way that it actually makes this matrix unitary. So what it does is it's going to make all these rows as well are going to become orthonormal. You get one more basis for free in some sense. It's a magic result which happens, which is you create one complete set of orthonormal vectors. You just put them all together in a matrix, and since the matrix is unitary, so you know that u dagger u is the same as u dagger. So whether you work with the vectors along this direction or the row vectors, they also have the same property. So until you get to the n minus 1th vector, you don't have it's not even obvious that there is this type of a structure happening, forming along the rows, but there is this inbuilt mechanism. So the moment you put this final vector in, all of these click, and then you have the same property operating along the rows as well, right? So it's like some magic trick which happens. Or in fact you can exploit this to even find the last vector. You have found n minus 1 of these vectors. You don't even have to directly find a final vector such that it is it's orthonormal to all of these. You can just try to fill out each of these elements along the rows such that each vector is normalized, right? So that's you can exploit this, right? So that's what it's a remark that I want to make about this. Okay, so how do we see this, right? I mean, I have already sort of jumped ahead and said a few things about this, but it's not a very difficult argument for why this is a unitary matrix, right? It just comes from the orthonormality property. So if we denote these column vectors as xi, in this manner, then we are given that xj xi is delta ij. That's the orthonormality property. Now in terms of the elements of this matrix, you can expand this and write it out. Summation over k, uik, ujk star, right? The star comes because you have taken the bra vector, right? So you have to do this complex conjugation, and then this is equal to delta ij. But if you look at this is the same as the condition for a unitary matrix. So U dagger U is equal to I, showing that it's a unitary matrix, right? So U dagger U equal to I is equal to U dagger, and so that's where you get this, the constraint between the row vectors also appears automatically. It clicks together in some jigsaw puzzle fashion. Okay, so the converse result is also of course true. If you started with a unitary matrix, then for sure the column or row vectors form a complete orthonormal set, right? So this is inbuilt into a unitary matrix. So you're given a unitary matrix, so this holds, and therefore you can write out the elements of the matrix. You have this relation, and this relation is the same as saying, if you denote these as column vectors, then this relation is the same as saying xj and xi are orthonormal to each other. So explicitly the condition of unitarity immediately implies that you have a bunch of vectors which form an orthonormal set, right? You could start with a unitary matrix and then pull out all the vectors, the row vectors or the column vectors, and say that you have a complete orthonormal set. Or you could start with an orthonormal set of vectors like we do often with Gram-Schmidt orthonormalization process, and then you can create a unitary matrix, right? So I invite you to use this property and play with Gram-Schmidt examples that you have already worked with. Take some three vectors, and they don't have to be orthonormal but linearly independent vectors, and then orthonormalize them using Gram-Schmidt, and then start filling in the columns, and then you see that magically they will all click in such a way that the row vectors also have this property. So we will see in the next lecture that this has a very important and useful consequence. Thank you.